What's going on, guys? It's the Unhinged Engineer here. I'm back today with episode 27 of our Georgia Tech OMSCS vlog, and today I'm talking about Project 1 of computational photography. So the title of the paper we had to implement is very, very long, so I'm just going to refer to this project as the object removal project. We had to follow pretty closely a specific method of object removal that's pretty old, back in like 2004 or 5, I think. I can't remember when the paper was written. But if you've done object removal on your iPhone, like a lot of that's just done with like super sampling with neural networks today. Like obviously NVIDIA and other GPU vendors have made that a lot easier. But back in the day, everything was like CPU based, and so they had to be a little bit smarter about how they threw compute around. And so we have to implement one of those like old methods of object removal based on the original paper in which it was written, and yeah, run it through a couple of test cases, talk about the images, etc., etc. If you've been following the vlog, you know the drill. I'm the Unhinged Engineer. I also make professional development content for engineers like myself who are early on in their career. I'm an aerospace engineer by trade, but I'm getting this degree in computer science at night. So if any of that content interests you, definitely like, comment, and subscribe to the channel. And let's get right into the exemplar-based Inpainting method of object removal project for computational photography. There you go. So, okay, what was this project about? Well, like I said, we had to implement a specific method of object removal as written in a paper by Criminisi et al. From I think 2004. Yeah, 2004. And so this is pretty different from what you might expect with something like a neural network, where you just pick a pixel, you do some super sampling around it, and like automatically generate new pixels to, you know, replicate what something should look like inside a target region based on what's surrounding it in the image. There's no neural networks or AI or fancy stuff like that in here. In a way, this technique is basically just constraint propagation, right? Where there's two main innovations, I think, here. The first one is this kind of priority system based on like a confidence term and a data term. So the confidence term is really, really straightforward. It's basically just kind of like how close are we to the boundary of what we know versus what we don't know. And what that enforces is this like kind of concentric going around the edge of the target region you're trying to inpaint. You kind of go around it, quote unquote, in order, this like spiral. So that's pretty straightforward, but does have some important implications to talk about a lot in the paper. So it's important to get that right. The other side is this like data term, right? Where the data term is effectively based on the isophote of the image, which an isophote of an image is like perpendicular to its gradient. So effectively what you're looking at is like, okay, do I have any structures like linear structures coming into the target region? And so if that's the case, I want to continue those structures as I paint into the target region, right? And that's really cool. And there's interesting capabilities that gives you, like if you cut out part of a street sign or a fence post or something, it will actually continue to, you know, propagate that structure through the target region, which makes it a lot more convincing. Versus if you just like slapped some color in there, you might have like the top half of the linear structure and then a gap and then the bottom half, which obviously we know doesn't make any sense, and so the whole thing's ruined, right? So you kind of use those two to weight it such a way that, you know, you're doing it in the normal, like what you would consider order, like spiraling down that mask so you fill it in uniformly, but also you're preserving some kind of linear structure. And so you take those two, you compute the priority, and that determines the order in which you're inpainting things. So that's one side of it. The other side of it is this SSD function, which is really, really straightforward. It's effectively like least squared error between two images in 3 channels, right? So what you do is you say, okay, once I pick the pixel that has the highest priority along that boundary line, I draw a patch around it, just like you would do with any other convolution or whatnot. And I pick that patch, and then I go through the known region of the image, and I say like what parts of the known image are the closest to that target patch, or I should rephrase, the parts of the target patch that are in the known image, right? So the target patch, kind of the center pixel lies on the boundary, and so part of it is outside the target region, so we're not trying to fill that in, it's just there, and then part of it's inside the target region, so it's unfilled, and that's what we're kind of creeping into, we're propagating into. And so you take that known part of the target patch, you compare it against everything else in the known image with the spatial sampling distance, and whatever has the smallest distance, you inpaint there. And again, using the language of neural networks, which if you're into this stuff but have only caught on to it recently like I have, this is what you're more familiar with. It's just like vector embeddings, except we don't actually have to do any fancy kind of transformation into a vector space. It already is in a vector space because we have a RGB component. That's a vector. You take the spatial sampling distance, so distance between that 3-dimensional vector and all the other ones for all pixels in that patch. You minimize it. That's the best match, right? Pretty straightforward. So least squared error in this context is called spatial sampling distance. And then you have the priority calculation. So you take those two together, and effectively what you get is you get a really smart way of taking a known image and slowly propagating it into the target region that you're trying to inpaint such that there's visual continuity. That's the point of the whole project. Apologies, it's a little convoluted. The paper is actually really good. It goes through everything in pretty good detail with some good diagrams. So I'll actually link that in the description in case anybody's curious. But yeah, that's what we were tasked to do. And effectively, you have to follow that to the T as closely as possible, which I pretty much did. You have to take that project or take that paper and implement it in your code. So there's a lot less structure in the coding environment they give you. Basically, they give you a runner for slotting in different images that you provide and running it through this object removal function. It's literally just called object removal.py. There's an additional component to that where you set the window size, because we were talking about patches and stuff. So you as a user can set the size of the patch that you're trying to compare to different things when you do that SSD calculation, among other stuff. And so it gives you a little bit of kind of parameterization that you can do, but that's basically it. Everything else is completely up to you. It's completely unimplemented. And so you are tasked with writing those helper functions for yourself, whereas previously we were tasked with we were given those helper functions and had to actually implement each of them one at a time. And in certain cases, that was even part of the autograder. Does each constituent step of this algorithm come out to the right answer as opposed to just the whole thing? Speaking of that, the autograder here was way less strict. So you kind of just checked if it runs. That's really it. Whereas, the autograder, I think overall in this class has been fine. It hasn't been too strict as far as I can tell, because basically it would just check if you're getting the right sized outputs, the inputs all line up, and then it would do some kind of checking if your answer is correct. From what I've heard, that's actually down to 10 to the 9th. So you have to be within 1 billionth to actually get it correct. And so I obviously am not, but I still get 47 or 48 out of 50, so I don't really care. But that would obviously be frustrating to some of our more perfectionist friends out there. In any case, this project has none of that. It basically just checks if your code runs. So who knows? I could have accidentally put terrible code in there. But I know it works. I know it works for all my images and for most of any other ones that I put in during testing or whatnot. So yeah, that's the autograder. Coding environment's pretty sparse. You basically have to implement everything yourself. And yeah, in terms of the images, you have to do it for 3 images. Same kind of deal where, it has to be your own images. The EXIF data has to be included. You can't just pull something off the internet. I did actually pull some things off the internet during training, as well as making test images in PowerPoint with kind of a red dot and, green region, just really basic polygons. I included those polygonal images in the submission. Obviously didn't include the internet ones because they're kind of batshit crazy about plagiarism. But anyway, I did include my own personal test images that I created. Any stuff I found on the internet just for testing was here's some dude standing in front of a building with a lot of linear structures coming into the target region, or standing in front of a fence. I actually tested on kind of what are they called? The Queen's Guard, where they stand in front of that fence, right in front of the palace, and then I checked that the fence post would come in behind their back if I remove the soldier or whatever. So stuff like that, right? But yeah, the algorithm itself is pretty interesting. I didn't really vectorize my implementation as much as I'd hoped, and a lot of these kind of more granular assignments, I've actually been getting a lot better at NumPy, and so that's kind of an unforeseen benefit of this class. But in this one, I kind of, the algorithm was complicated enough that I basically resorted to nested loops and stuff like that. And that's actually reflected in my computational pipeline, which I'll talk about when I get to the report section. So yeah, it's basically just a bunch of nested loops doing each of those checks of okay, does the mask still exist? And then beyond that, let me find the next patch I want to fill in, and then let me evaluate all the patches, all those different loops that you would expect from the algorithm based on the paper, I kind of just nested the crap out of it and called it a day, right? So yeah, but I got something that works. For the most part, it basically captures as much visual continuity as I could reasonably expect it to. Obviously, there are some discrepancies in the infill. It's not perfect, but I do think it looks pretty realistic. And actually, there is a final portfolio that you can release once the class is over. So maybe I'll show off some of those images at some point if there's interest. But yeah, I think the algorithm performed pretty well. That said, I don't have any way to actually gauge how well I'll do. And honestly, I'm okay with that because I don't feel like the auto grader enforcing it. So yeah, that's the code, basically just the algorithm. So that's kind of the same section of the video, really. I did have to do, I guess I'll say, I did have to do a couple of like hotfixes where, oh, maybe the sizes of the patches don't line up, or bugs caused by the mask extending towards the end of the image. So that would again cause like the patches to get messed up. Little things like that. I had to kind of implement these additional hotfixes, which weren't mentioned in the paper. So more likely than not, it's just a skill issue of like something I did wrong that I had to add this additional kind of cropping. But again, it didn't really affect the performance of my algorithm insofar as I can tell. They were pretty straightforward, right? So yeah, I did have to add some of that, and that's like in addition to the core algorithm. But like one of the sections in the report, which I'll get to in a second, was like, is there anything from the algorithm you didn't do or you were unable to complete? So I guess they're just kind of hoping you like self-report yourself if you didn't get something done and didn't get it done, as correctly as you would have liked. I don't know what the hell the section that section of the report is for, because if you don't finish everything, then the algorithm just doesn't work. So I don't quite understand. Maybe they're just trying to save themselves some work by having kids self-report for mercy. I don't know. Anyway, yeah, let's get to the report. So the report for this was pretty massive. I mean, while the coding was a ton of work, and I don't think that the report was like a disproportionate amount of work to code, it was basically equal, which meant that this project overall was a crap ton of work. In case you haven't been following, like the first assignment was really, really simple and the report was massive. So that was honestly kind of obnoxious to the point where like I literally had to make a cardboard box for my first project. It was like arts and crafts. And then the report was obnoxiously long and had to be obnoxiously in-depth. Then for the other assignments, it kind of had a good ratio of like, the report is commensurate with the amount of code you had to write. So you're not like role playing as an academic. You're just, writing an explanation of your code. It makes sense, makes logical sense. This project was basically the same. Like I think the ratios were good, but it was just a shit ton of work overall. So that's obviously a lot. They do give you a lot of time though. I think it's been like 2.5 weeks, something like that. So they give you a lot of time. I feel like it's a fair amount of time. Yeah, what were the sections of the report? Well, you had to go over, the algorithm as a whole, then go through it like in kind of more detail of like, okay, now that I've described the overall algorithm structure, kind of the way I just did for you in this video, you have to go into a deeper level than that, like actually show your code and explain what each function does and how it works and stuff like that. So that's called your computational pipeline section. And there's actually like a whole flow chart you have to create to go with that kind of shows that code flow. So effectively it's just the technical part. There's like the BS like academic description of the algorithm, and then there's actually going through the code and explaining how it all works. So I did think, while a little bit repetitive, they were different enough that it made some sense. Maybe the discussion of the algorithm section versus the pipeline, like maybe that discussion of the algorithm section was kind of unnecessary. I would just make it one mono section and go through everything all at once. But anyway, yeah, describe the algorithm, describe each of its parts. After that, describe development. Again, just like a ton of self-reporting of like, what were errors you found along the way? What were some, bugs and hotfixes you had to do? Blah, blah, blah. Just like tons and tons of I promise you I'm learning from this like content, right? Not really actually helpful content. So that was a little bit annoying. But, there were some interesting parts of it. Like I definitely think tweaking that window size was pretty interesting to see. Even though I'm kind of familiar with that concept from like convolutions and other things. So yeah, tweaking that window size was interesting. Those hotfixes I had to do were interesting because they were outside of the paper's original implementation. So it is good that they gave me a chance to explain that. Otherwise it would have kind of just been dangling there in the code. Wouldn't really have had a chance to defend the work I did. So that makes sense. stuff like that, just kind of describing what the process was like. And I actually tied that into my next section, which was on the images themselves, because what I did for this project, which I would recommend to anybody doing this in the future, hello future CS6475 student, I would start with a really easy image and then scale up from there. In their obnoxiously long assignment instructions, they talk about like all the images can't be the same visual content. And so I was really clear, like, okay, I'm gonna start with one dumb, easy image that literally I put a bottle on a table. That was it. And I tried to like remove the bottle while preserving the horizon line of the table against the wall in the background. That's it, like really dumb simple. And I'm sure like if I did that for all 3 images, they probably would have complained about it. They might still complain that one of them was simple, but I felt like it made sense to include the one I did the development with. So that was the first one I did. The next one was more complicated. It was kind of like a signpost in front of a natural scene. That stressed some edge cases I was talking about earlier. The content was also just visually more complex, and so it definitely stressed the algorithm out a bit more. Also, the mask was larger, so obviously like the larger the mask, the more that the algorithm has to inpaint, and so the higher the performance requirement on its actual like sampling quality is. Granted, the mask itself is kind of slender, which does actually help because you don't have to traverse as far. Like you go from one boundary to the other pretty quickly, and you just kind of keep filling in that order. But it was still larger. And the last one, like I actually had a deer in an image, and the deer was in front of like an artificial feature, like a wall, and then this big like flagpole, I can't even remember, like right in the foreground. And so and that extended from the grass on the bottom up through the wall, and then up through even like the trees in the sky above that wall. And so there's a lot going on, and basically I removed the deer and the pole. So another thing I wanted to test was like, can it handle a mask that's 2 separate regions? Like they're not connected in any way. So one's the deer and the one's the pole. So I was like, okay, let's really stress this algorithm. The mask is freaking huge compared to the image, and it's different shapes, go through different like visual content in the image. I felt like it was a pretty good real test case of the algorithm, and so that was my most complicated image. It was also my largest image and my largest mask. And I kind of documented like, okay, as I went from the dumb easy bottle example to the more complicated sign pole example to the most complicated scene with a deer and a pole and other stuff going on, what had to change, like some of those hotfixes, how the window size was different, how the algorithm performed differently, stuff like that. So that was the last section. And so that one and my project development one kind of not logically continued from one another. And so all this to say, the report was freaking long, but I do think it was fine. I think it wasn't an obnoxiously long report. The max amount of pages was 10, but you do like put in a ton of images. So mine was 8 all in with the images included. So maybe like 6 pages, 5 or 6 pages of actual writing, which again, is a lot, but for 2 or 3 weeks is not crazy. So yeah, I'll say overall, I did really enjoy this project. This class is like really frustrating, to tell you the truth, because like the content and the projects are so great, and then the written communication from the instructors is just like so freaking annoying and so off-putting, to the point that like it will probably single-handedly make me not take computer vision in addition to this class. I mean, I wasn't really planning on doing that just because it's kind of repetitive, but I would have been open to it prior to having taken this, but the whole way the course is run is just so annoying and aggravating, and as a result, like the Discord is completely dead. I don't feel comfortable reaching out to the TAs. I just don't think they do a good job running it. But the content and the stuff we're learning and the projects we're doing are all dope. So I kind of have like this is a very frustrating situation that I haven't been in the program. Granted, it's only my 3rd class, so maybe this is kind of a normal thing. But yeah, overall, I'll say the project was really, really good. And while I continue to have mixed feelings about the course overall, I think that this was worth the amount of work. Again, maybe the report was a little bit longer than would have made it, but not too bad. And so, yeah, I think I enjoyed the project through and through. So, yeah, that's basically it. Thanks a lot for watching. Sorry if this review was a little bit of a ramble, but I actually wanted to record myself after having just submitted it, because sometimes I catch myself like submitting the project and then writing a bunch of stuff and compiling my thoughts. And that's good, but it's less of a vlog in that case. And so I was like, oh, like I have a little bit of energy left, even though it's 9 p.m. at night. Let me just bang out the vlog right after having done it and get these like raw thoughts out there. So what's next? To be quite honest, I don't really know. I haven't been paying attention to anything aside from this project. I think the next part is HDR, which is like high dynamic resolution, high dynamic range. I haven't been paying attention. But yeah, this HDR assignment, some more notebooks, peer feedback for this project, stuff like that, kind of standard things that I'll pick up with in the next episode, the post-project recovery episode, I guess I should say. Yeah, we're coming into October now. Class again is good. Again, I have mixed feelings about it, but overall I think the content is really good, and that's ultimately what we pay for. So yeah, thanks a lot for watching. I'm the Unhinged Engineer. I make professional development content for young STEM people like myself. I'm an aerospace engineer by trade, and while I'm working in that industry full-time, I'm taking this degree program part-time and vlogging it, sharing it with you guys. So if any of that content is something that interests you, definitely like, comment, subscribe. This is the channel for you. Thank you so much for watching, and I will see you in the next episode.